Liquid crystals are state of matter, something between a solid and a liquid. If you look at solid molecules, and we are interested in chemistry of liquid crystals, they have a fixed direction and a fixed position. If you look at a liquid, it's all over the place. It doesn't have a position or a direction. Now, liquid crystal has some direction and not a fixed position. And we can play with it in the following manner. So the chemistry of what molecule we choose for liquid crystal is important. It should have the following. So it should be polar to extent. If you look at the nitrile group, this carbon is slightly positive, and if you look at nitrogen, it's slightly negative, and that makes it the polar. So it's essential for the molecule to be polar. Then we can apply some voltage and change the direction of these sort of molecules. It should look like a rod or a cylinder, and this tail here, which is 5 carbon and 11 hydrogen, gives us that opportunity. So it makes it rod shaped, and also what it does is between these molecules we need some space, so it doesn't let them pack well. So that's quite needed. Now the two benzene groups, these are known, each benzene group with a connection is known as phenyl. So this is biphenyl because we have two phenyl. This makes the molecule sort of strong, stable, and rigid, and it's not susceptible to stress such as UV or fluctuation of temperature. So in order to pick and choose a molecule for LCD, for liquid crystal display, the molecule should have the following sort of properties: be polar, have a long chain of carbon, and also to have stable benzene rings. Now, in order to recap, because it's important, I'm showing the same molecule and I'm posing the question the way IB likes to challenge you guys. They will give you the biphenyl, for example, and say, take the 3 parts of this molecule, dissect it, and describe why they are needed in order to give its properties. So the first, which I told you, is the nitrile group, the carbon, nitrogen, slightly negative, slightly positive. It's essential for it to be polar, so we can play with it with voltage and change its direction. In one direction, light gets transmitted through, in another direction, it's dark. The other part is the pentyl group, 5 carbon ring and hydrogen, 11 hydrogen, not rings, 5 carbons and 11 hydrogen. This gives you the rod shape, and also it stops from packing between the molecules, so it doesn't let them pack well. The biphenyl are the 2 benzene rings. It makes the molecule stable, adds to rod shape quality of it, and stability is going to not let the molecule decompose under stress, such as UV, pressure, temperature. Now, they might challenge you and give you a brand new molecule and say, what about this? Now, this is, it has 3 phenyl groups instead of a 2 phenyl that you looked up there, and they say it can show LC, liquid crystal behavior, at higher temperature than biphenyl. What is the answer? The answer is obvious. Just look at the shapes and see what extra you have, which is a benzene ring. Therefore, it makes it more stable, and it can function under higher temperature for it to be a liquid crystal without being decomposed. Now, the ability of a liquid crystal to transmit light depends on its orientation, and we have 2 kinds of liquid crystal molecules. One is thermotropic and the other one is lyotropic. Now, thermo, from its name, it's a molecule that changes direction, changes the liquid crystal behavior over a range of temperatures. So as you change the temperature, there is a portion of temperature that liquid crystal comes to life. Thermotropic is also known as pneumatic liquid. And pneumatic LC are those crystals that have rod shape and have some random direction, but still overall it's in one direction. So thermotropic are those rod shaped LC that function over a range of temperature. Then the second category is lyotropic, and you need to know this vocabulary. Lyotropic are those LC molecules that change behavior when their concentration is changed. For example, a soap molecule is a great example of that. Now, soap molecule has a hydrophilic head because it's ionic, so this side likes water, and it has a sort of a hydrophobic tail because it's hydrocarbons and doesn't like water. So this is hydrophobic, and this here is hydrophilic. Now, as you change the concentration of soap or detergent, then you can also change its property, and under one concentration it becomes liquid crystal. At low concentrations it forms micelles, and what happens, these are the hydrophilic heads that are facing water, and the tail is inside, and you have your oil molecule or dirt molecule being trapped in it. Now, if you increase the concentration of the soap in the given volume of the water, then you will form a bilayer, and the hydrophilics are on the other ends, hydrophobics are facing each other, and now you have a molecule that looks like a rod shape, and it will give you liquid crystal behavior. One other example that is given in your book, and I'm going to mention it because I'm not sure if you're being challenged on it this coming exam or not, is example of Kevlar, which was by accident discovered in DuPont. The lady chemist, I don't recall her name, she came up with it, and it's used in many fabrics, for parachute, for your bulletproof vest. So Kevlar is important, and it's lyotropic liquid crystal. The link between the benzenes are going to make it extremely strong. There is hydrogen bonding here between hydrogen and oxygens of each molecule of Kevlar, and also as you line them up as you increase the concentration. So it's a lyotropic liquid crystal. Now, the shortcoming of Kevlar is concentrated sulfuric acid can break all these bonds and denature them because it's going to protonate nitrogen and oxygen. Finally, I want to just bring this point out. I'm not sure if it's part of your syllabus, but it used to be. So how does LCD device sort of works? I'm not going to get into technicality, but it's the ability of these molecules and change of direction that they can let light go through or not. You can read through it. If the voltage is applied, it's a light screen, and if the voltage stops, then you have dark points, and you can control these areas by the way you're going to sort of position your molecules in it.